Okay.
Okay, let us begin. Hello, everybody, and welcome to a new session of our webinar of differential geometry, AmSur, or AmSul-Amsur. It's the same, it's commutative. But then I have the pleasure to introduce to you Giovanni Bazzoni from Università degli Studi dell'Insubria in Italy, that's near the Lake of Como. And he will talk today on G2 structures on nilmanifolds and their moduli spaces. But before Giovanni begins, let me remind you that in the chat you can find all the links which are relevant for this webinar, where you can join our WhatsApp group and the web page of the seminar and many other things. Okay, now it is done. Thank you, and go ahead, Giovanni. Thank you.
Okay, well, thank you, Adrian. Thank Enrique, and thank to all the organizers for this invitation. I'm really happy. I'd rather be actually in Cordoba in person because it's a very nice place, or also in Campinas. I mean, both are very nice places. But in the wait for an actual travel, I'm very happy to be online with you. And thanks again for the invitation. So the project that I'm going to talk about is based on two papers. One of them is with Antonio Garvín from Malaga and Vicente Muñoz, who was at the time in Malaga and now back in Madrid. And the second paper is with Alejandro Gil García, who is now a postdoc in Beijing. And at the time, oh, sorry. I don't know what happened. Are you still there?
Yes, we can see that.
Because my screen just went black. I don't know what happened. And Alejandro is now a postdoc in Beijing, but he was a PhD student of Cortés in Hamburg. So it's a mixed group of people. And I would like to just do some quick review of G2 structures on manifolds, just in general. And then I will explain which kind of G2 structures I'm interested in, and the spaces that I study G2 structures on, which are nil manifolds, as most of you know, compact quotients of connected, simply connected nilpotent Lie groups. The classes of structures that I'm interested in, for reasons that will become clear, given that the spaces that I care about are nil manifolds, will be closed and possibly purely coclosed G2 structures. And I will explain how to construct purely coclosed G2 structures from certain types of SO3 structures in dimension 6. And I will end up, also if time allows, saying something about their moduli spaces. So the moduli spaces of closed and purely coclosed G2 structures on nil manifolds. So let's start with just some review of G2 structures on 7 manifolds. This will be very basic, just to give you the flair if you're not a G2 guy or girl. A G2 structure on a smooth 7 manifold can be defined as a reduction of the structure group of the manifold, of the frame bundle of the manifold, from a general linear group GL7 to G2 viewed as a subgroup of SO7. Playing around a little bit, one can see that a G2 structure on a manifold is equivalently given by 3-form phi, which is pointwise equivalent to this very specific 3-form, which basically encodes the multiplication rules of octonions. And it's no big surprise because G2 is the group of automorphisms of imaginary octonions. And this inclusion of G2 in SO7 explains us that we can determine a metric starting from a G2 structure. So we denote this metric G phi, and also an orientation, because we are in the special orthogonal group, and we denote this orientation O phi. We denote by omega 3 plus the set of G2 structures, which is an open subset of the 3 forms. And in the, let's say, nomenclature of Spiro Carigiannis, we can think of a G2 package of a manifold M consisting of a metric G phi, an orientation O phi, and since we have metric and an orientation, we also have a Hodge star, so star, which also depends on phi. So some things about, for example, the existence of G2 structures on manifolds. So if you have a G2 structure on a manifold, of course, M is orientable. I just told you it has an orientation. And since G2 is simply connected, M also admits a spin structure. So, for example, we conclude from this that if a 7 manifold admits a G2 structure, both the first and the second C-field within classes vanish. Okay, it is a result, kind of classic result of Gray, that the converse is also true. So, if you have a smooth 7 manifold which has vanishing first and second C-field within classes, then you know that the manifold admits a G2 structure. So it's just, just a topology study if some bundle has a reduction, and this is quite clearly a topological question. For example, if you have a parallelizable 7 manifold, like the 7 sphere, this has a G2 structure, okay? One way in which one could come across G2 structures is from G2 holonomy. So just a brief reminiscence of what a holonomy group of a Riemannian manifold, connected Riemannian manifold is. This is just the subgroup of the orthogonal group, which is well defined up to conjugation, determined by the parallel transport along loops based at some point of the manifold. So you just parallel transport tensors or vectors along some loop, and this gives some automorphisms of the tangent space, and the collection of these automorphisms is the holonomy group. In 1959, in a paper which is classical by now, Berger showed that G2 is the only possible non-generic, generic would be SO7 holonomy group of simply connected, irreducible, non-symmetric Riemannian 7 manifold. The well-known holonomy principle says that a manifold with holonomy contained in G2 has a G2 structure phi, such that the metric induced by phi is precisely the metric we started with, and this 3 form is parallel with respect to the Levi-Civita connection of the metric. And moreover, the Ricci tensor of this metric is 0. So it's a Ricci flat Riemannian metric. Berger result was, as I stated it, is the only possible. Okay, so nobody knew back in 1959 if manifolds compact or not, complete or not, with Riemannian manifolds with a holonomy G2 existed. So we had to wait like over 25 years to get the first examples by Bryant in 1985, which were non-complete. They were turned into complete example by work of Bryant and Salomon a few years later. And we had to wait a little more for compact examples, which were constructed by Joyce in 1996. There have been more constructions, of which I would like to quote the one by Corti, Askins, Nordstrom, and Pacini in 2015, and a more recent one by Spiro Carigiannis and Dominic Joyce in 2021. In the language of G2 structures, one can consider different classes and try to classify G2 structures pretty much as Gray and Vella did for UN structures in their seminal paper on the 16 structures of almost Hermitian structures, 16 classes of almost Hermitian structures. So if you have a manifold endowed with a G2 structure, of course you have a metric, so you have a Levi-Civita connection. And one can see, and this is a result by Fernandez and Gray from 1982, that the 3 form is actually parallel with respect to the Levi-Civita connection it itself induces, if and only if the 3 form is both closed and co-closed. So the co-closed refers to the closedness of the Hodge dual. And remember, the Hodge dual is done with the G2 package, so with the Hodge star associated to the metric and the orientation. So another way to rephrase this result by Fernandez and Gray is that the holonomy of G phi is contained in G2 if and only if phi is both closed and co-closed. In general, whenever you have a G structure, you can define the concept of intrinsic torsion. And in this case, it turns out that the intrinsic torsion of a G2 structure is governed by the 4 form D phi, which is an element of it's a 4 form, which is isomorphic of the 3 forms using, again, the Hodge star. And the differential of the Hodge star of the Hodge dual of the 3 form, which is a 4 form, so its differential is a 5 form, but we're actually talking about a 2 form, again, using Hodge duality. So G2 acts naturally on the spaces omega-3 and omega-2 of 3 and 2 forms respectively, and one can decompose these spaces into orthogonal summands, for example, omega-2 7 and omega-2 14 concerning omega-2, and a trivial summand spanned by phi, pointwise by phi, for omega-3, with a second summand which is denoted classically by omega-3 7, and a third summand which is denoted omega-3 27. This refers to the pointwise dimensions of these representation spaces. For example, omega-2 14 is formed by the 2 forms which are annihilated by the wedge product with the 4 form star of phi, and omega-3 27 is just the 3 forms which are annihilated by both by the wedge with phi and by the wedge of its dual. More recently, Bryant has basically completely characterized the torsion of a G2 structure. So he's shown that if you have a G2 structure on a 7 manifold, then you can find 4 forms. So tau 0, which is a function actually, tau 1, which is a 1 form, tau 2, which is a 2 form in this specific summand of the 2 forms, and a 3 form tau 3, which is in this other specific summand of the 3 forms, in such a way that the intrinsic torsion, which is the differential of phi, and that of its Hodge dual, can be written completely in terms of this 4 torsion forms. So with this concrete expression, which I'm not going to read. So since there are 4 parameters, pretty much as it happens in Greyer-Veja classification, we obtain 2 to the 4 16 classes of G2 structures. And as we know, as it's classical, the holonomy of G phi is contained in G2 if and only if all the torsion forms vanish, because the vanishing of the 4 torsion forms is equivalent to the closeness of d phi and to the closeness of phi and of its Hodge dual, which by Fernandez-Gray is equivalent to the parallel to phi being parallel. That's why matrices with holonomy contained in G2 are also called torsion-free G2 structures. Okay. So holonomy G2, rephrased in terms of G2 structures, is torsion-free. What about allowing the first 1 degree of torsion? So a way of thinking of a possible way to do it would be, okay, I will allow just one of these torsion forms to be non-vanishing. So take 4, you have 4 torsion forms, pick 3, send them to 0, and just keep 1. If you do this, you obtain the so-called pure classes of G2 structures, which are, for your convenience, collected in this table. For example, if you ask only tau 0 to be non-zero, you obtain nearly parallel G2 structures, which are characterized by this differential condition. D phi is equal to tau 0 times the Hodge star of phi. Then you have locally conformally parallel LCP G2 structures. You have closed G2 structures, which are characterized by the condition of d phi, for example, being 0. That's why the term closed. And d star phi being tau 2 wedge phi. And you have the purely coclosed G2 structures, which are characterized by being coclosed, meaning that the star of phi is closed, plus some extra datum. So in this case, d phi is the Hodge dual of tau 3. So let's remember briefly what these special classes of pure G2 structures are. For example, let's talk about nearly parallel G2 structures. They've been studied extensively in 1997 in a paper by Thomas Friedrich, Ines Katt, Andrei Moroianu, and Uwe Semmelmann. And it turns out they can be equivalently defined in terms of a Killing spinner. They have Einstein underlying Riemannian metric. And for example, they do exist on the sphere S7 and on many homogeneous spaces. So I told you before that the sphere S7 being parallelizable admits a G2 structure. Well, we also know that it admits a nearly parallel G2 structure. Concerning locally conformally parallel G2 structures, if the manifold is actually simply connected, it turns out they can be rescaled to give torsion-free G2 structures. So they are globally conformal if the manifold is simply connected to actually torsion-free G2 structures. If the manifold is not simply connected, nevertheless, but it's compact, you have a strong structure result by Ivanov, Partone, and Piccini, which says that on a compact manifold, locally conformally parallel G2 structures are actually equivalent to mapping tori of compact simply connected nearly Kähler 6 manifolds. Remember, mapping torus is just of a manifold. It's just pick a manifold, pick a diffeomorphism, and identify n, or this manifold at time 0, with the manifold at time 1. So multiply the manifold by the interval and identify the manifold at time 0 with the manifold at time 1 by using this diffeomorphism. And this is the structure result by Ivanov, Partone, and Piccini. As for closed G2 structures, one of the reasons why people care about closed G2 structures is because both Joyce's construction and Joyce-Carigiani's construction of holonomic G2 manifolds start with a closed G2 structure on a manifold orbifold. So with some hard tools from analysis, they are able to deform a closed G2 structure to a torsion-free one on a space which is not necessarily a manifold. But they are sort of the starting point of many constructions of holonomic G2 manifolds. They are interesting because they do define calibrations in the sense of Harvey laws. So if you take any three-dimensional subspace of the tangent space of a manifold M with a closed G2 structure, then the restriction of phi to this three-plane is smaller than or equal to the volume defined by of the Riemannian volume defined by G phi. And sometimes these closed G2 structures are thought of as the analogon in G2 geometry of symplectic geometry. We'll see a little bit more about that later. And for example, a basic open question which sort of tells already apart the symplectic case from the symplectic G2, sort of from the closed G2 setting, is that it is not known whether there can be exact G2 structures on compact manifolds. By exact G2 structure, I mean a G2 structure whose defining three form is not only closed, but it's actually exact. Okay. Of course, for symplectic geometry, we all know by Stokes' theorem this is not possible on compact manifolds. But this is so. The reason for this is that the relation between the volume defined by a three form, by a G2 three form, is highly nonlinear, whereas it's linear for the volume defined by a symplectic form. For example, we don't know whether the seventh sphere admits a closed G2 structure. Okay. Which would automatically be exact if it existed, because S7 has no third Betti number. Let's move to coclosed G2 structures.
Can I ask you a question?
Sure.
I'm only asking you this because you're you. I don't think it's a proper question to ask of the general speaker. If the seventh sphere were to admit a closed G2 structure, would that imply an answer to Hoppe's conjecture for S6?
I am not completely sure about that, but it's possible. Let me think. So you can take a hypersurface of a closed G2 structure, and would that be automatically complex? I'm not sure.
Yeah, I think you could go like this. The coefficients of your phi ijk could be the structure functions of a global frame on S7, which would correspond to the existence of a torsion-free J of an integrable J.
Torsion-free on the equator of the sphere.
Yeah, on the equator.
Yeah. Something like that. Yeah, it's probably. I mean, I don't know if it's equivalent, but it's definitely related.
Okay, cool.
Okay, thank you. So as for coclosed G2 structures, They're not a pure class, but they contain both purely coclosed and nearly parallel G2 structures, because coclosed G2 structures are simply defined by the fact that the 4-form star of phi is closed. Okay, they are naturally existing on hypersurfaces of Riemannian 8 manifolds with holonomic spin 7. And as it turns out, they are not really hard to obtain, because we have a kind of H-principle result proved by Crowley and Nordstrom in 2012. They prove that if you have any 7 manifold with a G2 structure, then you can basically not promote the structure you have, but you can definitely find on that manifold also a coclosed G2 structure. Okay, so this is an H-principle type of result. In the homotopy class of any, whatever that means, of any G2 structure, you also find a coclosed one. Okay, so coclosed G2 structures are not very hard to obtain. For example, every parallelizable 7 manifold admits a coclosed G2 structure because it admits a G2 structure. So in this talk, we will focus on manifolds with purely coclosed G2 structures. Okay. Where do we try to construct these structures? Well, on basically nil manifolds. So I'll just give a brief overview of nil manifolds. So for this, I just need to recall you what a nilpotent Lie algebra is. Well, given any Lie algebra, G, you can define the ascending central series, which starts by putting G0 equal to 0. And then G, K, inductively defined, is formed by those vectors in G, which, when you bracket them with all the vectors of G, they fall into GK minus 1. Okay. So it turns out easily that every GK, these are nested in one another, and all of them are ideals in the subsequence. Of course, the first G1 is just the center of your Lie algebra. And if this ascending central series eventually fills the whole G, so if you find some n such that Gn is equal to G, then the Lie algebra, you call it nilpotent. And you say that the Lie algebra is m-step nilpotent if you don't fill G at step m-1, but you do fill it at step m. Okay, in this case, m is the nilpotency step of G. So for example, you could have an abelian Lie algebra, in which case G1 would be already the whole space, and then abelian Lie algebras would be one-step nilpotent Lie algebras. So the first interesting nilpotent Lie algebras would be two-step nilpotent Lie algebras, which have a very rich theory. Usually, I shorten the notation to NLA. They all have non-trivial center. This will be important later when I describe my construction, because G1 is non-trivial and it's the center. So a Lie group is nilpotent. Let's take it connected and simply connected. It's nilpotent if its Lie algebra is. Topologically, nilpotent Lie groups, if they're simply connected, they're not really interesting because they're all diffeomorphic to Rn for some n, which is the dimension, of course, of the Lie group. So if you're interested in obtaining something compact from a nilpotent Lie group, you may want to do like this. You take a lattice, so discrete co-compact subgroup in nilpotent simply connected Lie group, and then you just form the quotient. Okay, so that's a nil manifold, which by construction is, in my definition, compact. Okay, so nil manifolds are just the quotients of nilpotent simply connected and connected Lie groups by discrete subgroups whose quotient is compact. So a way to check whether connected and simply connected nilpotent Lie group admits a lattice is just given by Malchev. It's very simple, and it says that this happens if and only if G admits a rational structure. So G is actually the realization of a rational Lie algebra. A more down-to-earth way of thinking about this is just asking for the existence of a basis of your Lie algebra with respect to which all the structure and constants of your Lie algebra are rational numbers. Okay, so just check your Lie algebra, and if the constant structures are rational, then you immediately know that there is a lattice inside it. Basically, the projection from G, the Lie group, to the nil manifold is the universal cover. And since G is diffeomorphic to Rn, nil manifolds are spherical spaces. And the first sort of the fundamental group of G over gamma is just gamma. And a very important result, which turns the computation of cohomology of a nil manifold into an algebraic problem, is Nomizu theorem, which says that if you have a nil manifold N, which is G over gamma, you can, of course, include the exterior algebra on the dual of G, C. So this is just left invariant forms on G, and you can push them down to N. So you have an inclusion. And it turns out that this inclusion is a quasi-isomorphism, which means that if you compute the cohomology of basically the Lie algebra cohomology via the Chevalier-Eilenberg model of G, this is just isomorphic to the cohomology of the nil manifold, or basically use this reversal. So if you want to compute the cohomology of the nil manifold, you just compute the cohomology of the Lie algebra. So let's now put the two things together, G2 structure on nilpotent Lie algebras and nil manifolds. As I already anticipated, well, nil manifolds are parallelizable because they're discrete quotients of Lie groups. So every 7-dimensional nil manifold admits, in principle, a G2 structure, but thanks to Crowley and Nordstrom, also a G2 structure. But we are a bit more picky, so we're interested in G2 structures which come from the Lie algebra. So which come from G2 structures on the Lie algebra, which give left invariant G2 structures on the Lie group, which are mapped to what one usually calls invariant G2 structures on the nil manifold. So let's just consider Lie algebras. A real Lie algebra with of dimension 7G, a G structure on this G is just a 3-form for which one can find a coframe such that the 3-form is written exactly as the 3-form that I gave you at the beginning, okay? With this strange expression which codifies the multiplication of imaginary electronians. And the kind of structures, G2 structures we want on 7-dimensional nil manifolds are precisely the ones induced by G2 structures on the Lie algebra of G via this inclusion of forms on G, on the Lie algebra, which are promoted to left invariant forms on the Lie group and then pushed down to forms on the nil manifold. Okay, and we call these G2 structures left invariant. What about G2 structures on nil manifolds? Okay, if you have a nil manifold which is not a torus, of course a torus is a nil manifold because it is a question of an abelian Lie group by a lattice. Nil manifolds cannot carry torsion-free G2 structures. Okay, not just left invariants, any. Okay, so nil manifolds never have torsion-free G2 structures. Also, they cannot carry left invariant nearly parallel G2 structures. And this is due to Milnor, because Milnor proved that a non-abelian nilpotent Lie algebra cannot carry an Einstein scalar product. Remember, nearly parallel G2 structures are Einstein. And nil manifolds also cannot carry locally conformally parallel G2 structures of any type, not just left invariant. And this is done by using the structure result of Ivanov, Parton, and Piccini, because just playing around with this mapping torus structure of this LCP G2 structure, the first Betti number of this manifold should be 1, but it's easy to prove, for example, using Nomizu theorem, that a nil manifold always has the first Betti number of at least 2. So we cannot find any of these structures on nil manifolds. So basically, if we stick to left invariant pure G2 structures, we are left with closed and, let's say, purely co-closed G2 structures on nil manifolds. What about G2 structure, closed G2 structures on nilpotent Lie algebras and nil manifolds, where there is a classification of 7-dimensional nilpotent Lie algebras by Gong. It's a pretty awful long list of 140 Lie algebras. plus 9 one-parameter families, and there are also 35 decomposable nilpotent Lie algebras. So there is a pretty big bulk of nilpotent Lie algebras. And Diego Conti and Marisa Fernandez proved a few years ago that only a few of those 12 up to isomorphism admit a closed G2 structure. Okay, so of all this almost 180, more than 180 Lie algebras, only 12 admit a closed G2 structure. So this gives the feeling that having a G2 structure, closed G2 structure, is, it's not just so simple. Okay, and since we now have a list of at least 12 nilpotent Lie algebras with a closed G2 structure, we can consider those as closed G2, left invariant G2 structures on the Lie group, and then consider them on the corresponding nil manifold, because we know how to decide whether a Lie algebra admits a lattice. So we obtain many nil manifolds with closed G2 structures. That's the corollary, the sort of heuristic corollary. There are many examples of nil manifolds with left invariant closed G2 structures. Okay. What about co-closed G2 structures? Well, we know the nil manifolds admit co-closed G2 structures. So what about left invariant co-closed G2 structures? We are a bit more picky, as I said. So in 2017, Bagaglini, Fernandez, and Fino proved that 25 out of 35 decomposable 7-dimensional nilpotent Lie algebras admit a co-closed G2 structure. Decomposable, I should have said that before, means that your Lie algebra can actually be written as the sum, as a direct sum of Lie algebra of a smaller dimensional Lie algebra with some abelian factor. Okay, and restricting to 7-dimensional indecomposable 2-step nilpotent Lie algebras, they turn out to be 9, and 7 of them admit a co-closed G2 structure. And further, they studied that all of those admit co-closed G2 structures induced in nil solitons. Okay, these results are obtained using Gong's classification, and Bagaglini, in an unpublished paper, tackle the other cases. So indecomposable of nilpotent step at least 3. But the paper does not seem to be complete, and Bagaglini has left mathematics, so the paper has never been published. So what about purely co-closed? Purely co-closed is a possible pure class which might exist on nil manifolds. So in this setting, there was a nicer, at least nicer, and I'm going to say why I think it's nicer, approach by Del Barco, Moroiano, and Raffero in 2022. They considered 7-dimensional 2-step nilpotent Lie algebras decomposable and not. And they proved that all those that admit a co-closed G2 structure also admit a purely co-closed one, except for one, which is the direct sum of H3 plus R4. H3 is the Heisenberg Lie algebra. So it's the Lie algebra of the matrix group of upper triangular matrices. Okay, and why I say it's nice, or nicer even, is because they do not use Gong's classification. They rely on powerful results for the structure of metric 2-step nilpotent Lie algebras. So such theory is not available for 3-step nilpotent Lie algebras, but for 2-step nilpotent Lie algebras, there is a very nice theory. So we know about co-closed, some things about co-closed and some things about purely co-closed. We don't have the whole picture. Okay, so we're left with some open questions. What about purely co-closed G2 structures on decomposable Lie algebras, nilpotent Lie algebras with nilpotent step at least 3? What about co-closed and purely co-closed G2 structures on indecomposable nilpotent Lie algebras with nilpotency step at least 3? So these are open questions which are left open by the papers of Fino, Fernandez, Fino, Raffero, and Del Barco, Moroiano, Raffero. So that's what we do. We study the existence of co-closed and purely co-closed G2 structures on nilpotent Lie algebras of nilpotent step 3 and 4. We could go on. There is also nilpotent step 5 and 6. But as you'll see, our approach goes through Gong's list. And purely coclosed G2 structures appear to exist in a lot of examples. So there's no other nice way to say it. We got a bit bored because all these cases costed us kind of a lot of work. And then put in step 5 and 6, just, we didn't feel like doing it. But so we concentrated on step 3 and 4, which already was kind of a lot of work. So to do this, we have to be able to, perform 2 tasks. The first task is a way to construct purely coclosed G2 structures on a nilmanifold algebra. And once I've tried quite hard for a while to do that, and it doesn't work, you have to be able to prove that a given nilmanifold algebra does not admit any purely coclosed G2 structure. So for this, you need obstructions to the existence of this structure. Okay, so in this next 2-3 slides, I will become slightly technical. So before you disconnect and you can come back in like 3 slides, just keep in mind that the way in which we decided to construct these structures, these purely coclosed G2 structures in dimension 7, was to do something with SU3 structures in dimension 6, and then extend it to dimension 7 with a 1-dimensional extra factor. So what I'm going to do in the next 2 slides is to briefly present SU3 structures, and in the 3rd, 4th slide, I'm going to explain how to use them to construct R structures. Okay. So just keep in mind that there is a strong relation between SU3 and G2 structures, and that's what we use to construct our purely coclosed G2 structures. So it's a bit more technical, but I'll be brief. Take a 6-dimensional real vector space. For a fixed 3 form, you can define a map from the vector space V to 5 forms on element of the 5th exterior power of V star, which is just given an X, you contract tau with X and you wedge with tau. So there is a natural isomorphism between V tensor, the 6th exterior power of V star, and the 5th exterior power of V star, which is given by contracting an orientation with a vector. And this has an inverse, which we call mu, from the 5th exterior power to, of course, V tensor with the 6th exterior power of V star. So composing K tau with mu, we obtain a map from V to V tensor wedge 6. And we can basically take, again, K tau, big K tau, and this determines a function lambda from the 3 forms to the second tensor power of the 6th form. In this way, you just take KT, you compose it with KT tensor identity, you take the trace of this endomorphism, which is an element of the 6th exterior power square, and you divide by 1/6. Okay, this is basically it's a real number, but it lives in some strange vector space. But it lives in a 1-dimensional vector space. So you divide the 3 forms on V star according to whether this lambda is positive or negative. Okay. So once you pick a psi minus in those 3 forms on which lambda is negative, it turns out that if you normalize this endomorphism K psi minus with some factor, which is given by this lambda, this gives an almost complex structure on V. And using this J, you can define a psi plus, which is minus J star of psi minus. Okay. Also, you can single out the 2 forms, so the elements of the 2nd exterior power of V star, whose 3rd exterior power is non-zero. So basically the symplectic forms, okay? Because we're in a linear setting. And then you can take a pair omega psi minus, where omega belongs in this space of, let's say, symplectic form, and psi minus belongs to these, let's say, negative 3 forms, with a further condition, which is the wedge product of psi minus with omega should be 0. And the tensor H, which is defined by using omega and J, is positive definite. Okay. Once you've done this, well, you have an SU3 structure on V. This is not the most, direct way to define an SU3 structure, but it's the one that I need. Of course, one could define an SU3 structure just as a reduction of the structure group. I mean, we're in a vector space, but on a manifold, of course, we could just, argue, as in the case of G2 structures, as a reduction of the frame bundle, blah, blah, blah. But that's the definition I need. The metric H, which is positive definite, and is, of course, symmetric, is the corresponding SU3 metric, okay? So using these SU3 structures, I will explain to you what we did in order to produce some purely coclosed G2 structure. So start with a 7-dimensional Lie algebra, not necessarily nilpotent, but you do need that its center is non-trivial, which is, of course, verified for nilpotent Lie algebras. Take a codimension 1 subspace. I denote it by V because this will be 6-dimensional, and on this V, I will put my SU3 structure, okay? And I fix a vector X which co-orients V, and I want this vector to be in the center of G. That's why I need a non-trivial center. Take a 2-form wedge 2 of G star and psi minus in wedge 3 of G star, such that when I construct those with this vector X, I obtain 0, and such that they define an SU3 structure on V, okay? If I, formally denote by putting a little bar the pullbacks of omega and psi minus to V, since I want them to define an SU3 structure, I have, that omega bar is in wedge 0 V star, and this lambda 0 V star, psi minus bar is negative, and omega bar wedge psi minus bar is 0. So I know how to determine a psi bar plus, which is an element in wedge 3 of V star, and I extend this psi plus to the whole wedge 3 of G star. I just declare that if I plug into X, I want to obtain 0, okay? And the final step of this construction is to pick eta in G star, which pairs non-trivially with this central vector X. Then the claim is that this 3-form phi defined by omega wedge eta plus psi plus is a G2 structure on G. The metric is precisely the SU3 metric H plus eta square. And the dual of this, of course, since we know the metric, we know the dual, the Hodge dual of this phi is just omega squared divided by 2 plus psi minus wedge eta. So the theorem is that this G2 structure is coclosed if d psi minus is 0 and omega wedge d omega is psi minus wedge d eta. This is just trivial computation. Furthermore, this phi is purely coclosed if omega square wedge d eta is just minus 2 psi plus wedge d omega. So, we can just take the list, try to produce this subspace V co-oriented by blah, 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 and, find adequate SU3 structure and promote it to a G2 structure. And we could do that on many 3-step and 4-step nilpotent algebras of dimension 7. For the computations, which are quite complicated, they're trivial because it's linear algebra, but, kind of elevated linear algebra. We used Sage Math, which is free. As I briefly explained, in order to make sure that if you have a certain nilpotent algebra which seems not to admit any coclosed G2 structure, you need actually prove it does not admit any, you need an abstraction. There have been 2 abstractions found by Bagaglin, Fino, and Fernandez. With Garvín and Muñoz, we found a 3rd one. So we were able to rule out with these 3 abstractions all the cases in which our construction was not possible, was not working, okay? So all in all, using Gong's list, our construction theorem, and the abstractions, we have that, for example, this result, every 7-dimensional decomposable nilpotent algebra admitting a coclosed G2 structure also admits a purely coclosed one, except for H3 plus R4, not just the two-step decomposable. And every 7-dimensional indecomposable nilpotent Lie algebras of nilpotency step at most 4, which admits a coclosed G2 structure, also admits a purely coclosed one. So in this sense, being purely coclosed does not seem to be much different from being coclosed in this setting. Notice that these results are okay. They might be okay or not. You may like it or not. But one thing I do not like myself is that in order to prove such a statement like every 7-dimensional decomposable nilpotent Lie algebras admitting a closed G2 structure also admits a purely coclosed one except for H3 plus R4, you need the classification. It would be very nice if you were able to single out H3 plus R4 by some, abstract reason, but we don't see that reason. We have to go through the classification, and this is kind of, not nice, but it's fine. Whatever works. Conti and Fernandez were able to prove that only 12 of the 184 nilpotent Lie algebras admitted closed G2 structures. The large majority of 7-dimensional nilpotent Lie algebras admits purely coclosed G2 structures. And we actually expect, it's not a conjecture, but our expectation that if we continue our study to 5- and 6-step nilpotency step, we see the same pattern. All indecomposable 7-dimensional nilpotent Lie algebras which admit a coclosed G2 structure, they also admit a purely coclosed one. Okay, so that's our expectation. A question which one may want to ask is, okay, I've told you before about exact G2 structures as those closed G2 structure whose 3 form was not only closed but also exact. One can play a little bit the same trick by requiring not the 3 form but the 4 form to be exact, in particular closed. The ones we constructed were not of this type. Okay. As I said, the question is open for closed G2 structure. In a paper by Anna Fino, Lucia Martin Merchan, and Alberto Rafero, they proved that no compact quotient of a Lie group by a discrete subgroup, not necessarily nilpotent, any compact quotient of a Lie group by a discrete subgroup admits an exact G2 structure, which is left invariant. And our conjecture is that the same should happen for coclosed. So no compact quotient of a Lie group by a discrete subgroup admits an exact purely coclosed G2 structure. Okay. We don't know that. And in the last few minutes, I would just like to say something very briefly about a study we did with Alejandro on moduli spaces of G2 structures. So if you have torsion-free G2 structures, which, as I told you, are equivalent to holonomy G2 structures, holonomy G2, sorry, then you can define on a compact manifold, you can define the Teichmüller moduli space of torsion-free G2 structures just as the quotient between the 3 forms, which are G2 type forms, so this omega 3 plus, and which are closed and co-closed by the action of the identity component of the diffeomorphism group. And a theorem by Dominic Joyce from '96 says that this space is a smooth manifold of a dimension B3 of M. Okay, and actually there is a kind of a period map which gives a local diffeomorphism of this MM to the third cohomology, the third de Rham cohomology. So, we can try to play the same game. What about moduli spaces of closed G2 structures? So you just forget about being co-closed and you take a compact 7 manifold with a closed G2 structure. Then the Teichmüller moduli space of closed G2 structures is just, the type 2 G2 structures, so phi in omega 3 plus, which are closed, mod out by the action of the diffeomorphism group. But as it turns out, this space is infinite dimensional. Just to give you an idea of why this could be surprising at a first glance, is that if you have a compact symplectic manifold, the moduli space of symplectic structure, which is defined in precisely the same way, so symplectic, so almost symplectic forms, which are also closed, mod out by the diffeomorphism group, this is actually a smooth manifold of dimension B2. So this result is kind of the equivalent in some sense of Joyce result. torsion-free G2 structure. So in this sense, symplectic and closed G2 are not alike. So one should be careful when saying that G2 structures are closed G2 structures are like symplectic structures. They have some similarities, but they also have some differences. We work with Lie algebras. So one thing we could do is just consider moduli space of closed G2 structures on a Lie algebra. So you take a 7-dimensional Lie algebra with a closed G2 structure, and then you consider all 3 forms which are closed and are of G2 type, and you mod out by the action of the automorphism group of G. We are like in the left invariant contest here. And we proved with Alejandro that if you have a nil manifold, then this modular space of closed G2 structure on the Lie algebra of G, you have a natural inclusion of this space into the sort of Teichmüller moduli space of closed G2 structure on N. So this infinite dimensional MC of N contains a copy of this MC of G. So a full copy, because it's an inclusion. So for the modular space of torsion-free G2 structures, the dimension was precisely the 3rd Betti number of the manifold. So one can ask if the dimension of this finite, let's say, finite dimensional approximation of MCN, it's improper. It's just a full copy. But let's call it, for the purpose of this talk, just finite dimensional approximation. If this dimension is related to B3 of the nil manifold, which is B3 of the Lie algebra by no-Mitsu theorem. And the answer is negative. So there is no relation between the dimension of this MC, modular space of, let's say, left invariant, one can think of left invariant G2 structure on N, and the 3rd Betti number. So we have results like, well, if G is decomposable, the dimension of MC of G is always smaller than the B3. And if the Lie algebra is intercomposable, you have both. You have both smaller than the B3 and bigger than the B3. Okay, we are in the closed setting. You can play the same game for co-closed G2 structures. They also have infinite dimensional Teichmüller moduli spaces, and there is no relation with the B3 and B4. So there seems to be no, let's say, invariant of which is finite dimensional invariant, which can be computed for this specific classes of G2 structures on nil manifolds. Okay. And I would like to finish with the last result, which we came across with during the proof of this theorem with Alejandro. So whenever you have a 7-manifold which has a G2 structure, you can consider the automorphism group of this phi, which is precisely formed by the diffeomorphisms of M, which pull back the 3 form to itself. Okay. And it's a nice result by Podestá and Raffero from 2018 that if you have a 7-manifold endowed with a closed, not just any, closed G2 structure phi, then the Lie algebra of the connected component of the identity of this automorphism group is abelian. Okay, so morally, the automorphism group of closed G2 structure is abelian. And with Alejandro, we were able to prove that if you have a co-closed G2 structure, well, the automorphism group, even in the compact case, does not need to be abelian. So this marks a difference between the closed and the co-closed case. And we came across it because this example is, of course, a nil manifold with a co-closed G2 structure, which admits 2 diffeomorphisms which preserve the G2 structure, but they don't commute. Okay, so the group cannot be abelian. And this is all. Thank you very much for your attention. I'm going to stop sharing.
Okay, thank you very much, Giovanni, for this very nice talk.
Thank you.
And now it's time for comments or questions. Does anybody has a comment or question for Giovanni?
I have a very quick one before Enrique asks his question.
Sure.
Do you know if there's some sort of homotopy classes of these G2 structures. I mean, does it make sense? Or
what do you mean by this exactly?
I mean, you can see them as sections into this the bundle, as you mentioned at some point, and then I wonder whether you can have different, in some cases, different homotopy classes of these sections.
That I don't know. No, I don't know. I'm sorry.
You
refer to the sections which give the reduction.
Yeah, exactly, precisely.
Yeah. No. I mean, it's a typical obstruction theory result. So I don't really know if something more can be said. No, I'm sorry.
Okay, thanks.
You're welcome.
Enrique, you raised your hand.
Yeah, maybe just 2 comments. So this is great, and I was actually trying to take notes of the last bit where you state the results, but you went rather fast through that.
Yeah, I noticed that I was sort of running out of time, so I'd be more than happy to share my slides if you want them.
Yes. But yeah. So the survey at the beginning was very nice too. So I think the students will benefit a lot from that survey, and so that was also great. But maybe we can look at just give another minute or two to just go over your results. If you can kind of summarize, where are we at? So you guys were able to, if you could, into, there's for step at least 4, there's something, and then for the what
we know so far, and there was a slide which tried to summarize everything, probably was apparently not effective enough, but I'd be happy to go over it. So we know everything for decomposable. We know that we know all that admit purely coclosed structures, and we know that there is only one exception, which is the Heisenberg algebra plus R4, which admits a coclosed but no purely coclosed.
Yeah.
As for the indecomposable, we know everything up to nilpotent step 4. We know exactly those that admit purely coclosed. We know that this class coincides with those admitting coclosed, and we know, of course, those that do not admit. So,
just to wrap up. So, among the sort of overarching question is, the problem is, among those nilpotents which admit coclosed, do they also admit purely coclosed? Right?
Yes. That's what we think. That's our feeling, because if you think about this extra condition that you need to pass from coclosed to purely coclosed, it's a small condition. It's a one-dimensional condition. So it seems that if you can solve the equation for coclosed, it seems possible that you can solve it also for purely coclosed. Of course, maybe not with our recipe. It's possible that our construction doesn't work, and still there is another way to construct a purely coclosed G2 structure. That's why obstructions are important, and we don't have any obstruction to purely coclosed. So what we say is that you don't admit any coclosed, hence any purely coclosed. But we don't have any obstruction directly for purely coclosed. Okay.
So when you say it's a one-dimensional condition, it's because that's just the tau naught, right? That's just tau 0.
Exactly.
Right.
Yeah.
So, all right, cool. And I was kind of interested in this comment, which you also kind of said it laterally, but it struck me as somewhat profound, right? That closed G2 are really not the same as symplectic. Because naively, if you contract the G2 structure with a vector field, you get a family of symplectic guys, right? So the 2 forms you get by contractions are all symplectic. And so when you're thinking about like something 6-dimensional inside something 7-dimensional, you're saying that somehow the way that 6 sits inside the 7 somehow makes the moduli space infinite dimensional, and that's a bit harsh.
I mean, it's really harsh also because symplectic has no metric and G2 has a metric. So, you're taught to think of metric objects as being rigid and of symplectic objects to be flexible. And so to me, to be completely honest, we didn't know that this was infinite dimensional. So we acted as if this was a honest, an honest finite dimension. And then somebody said, it's folklore. Everybody knows that. Well, everybody except us. And the proof is super simple. It's not really deep. It's just you write down the sum, and this is infinite dimensional. So there's no escape from there. So I don't have any feeling of what happens there. It's very, very surprising. It was when we found out, I was kind of surprised. Yeah.
Right. And last but not least, I don't know if you're familiar with the progress Thibault Langlaire, I think he's a student of Jason Lotte, has been making on studying the modular space of G2.
Probably not. Probably not. I barely scratched the top of the iceberg by quoting this Joyce result. So.
Right. So of course he's not in the context of in the sort of algebraic context, right? He's in the sort of in general.
Sure.
But it might be worth having a look at how Thibault's business specializes to the algebraic setting, because he's been making progress in the sort of description of the G2 structure modular space on a compact, arbitrary compact manifold.
Okay.
And this is recent stuff. He showed it to me in France a few months ago.
Okay. Okay. So that's really interesting. Yeah.
Yeah. If you guys can have a look, maybe this will specialize to something useful, precisely at this point where you were exploring.
Yeah.
Sort of modular space or technical space.
I mean, the result we can prove is very specific to nil manifolds, because the fact that there is this full copy of this sort of algebraic moduli space is very specific. It uses a theorem of, I forgot the name of the guy, Wilson, I think, which says that just for nil manifolds, you have this kind of behavior. I mean, you don't have it for solved manifolds in general. So,
yeah. Oh, sorry. Yeah, go ahead.
No, so I'm just saying that we are able to prove it in a kind of, small setting, but still broad enough to, maybe be able to say something. So yeah.
My idea would be that his stuff, which is kind of agnostic to the context, might bear implication into your stuff. It could specialize into valid results.
Yeah, that's really nice. That's super interesting. So yeah, well, maybe I'll write to you, and then you can pass me the exact references so that I can go directly to it.
Yeah.
Yeah, that would be really nice. Thank you.
All right.
Okay. Are there any other questions or remarks? Well, I do have one about solved manifolds with G2 structures. You said that there is no LCP G2 structures on nil manifolds because if the first Betti number should be 1, and that cannot happen for nil manifolds.
Yeah.
Solved manifolds can have Betti 1 equal to 1.
They can.
But do you know if there is other abstraction for those, or there could be some LCP G2 structure?
I mean, it depends on what you're looking for. In principle, I mean, this Parton result, the part of this Ivanov-Parton-Piccini result I use is just like a very small one, which is just that this mapping torus has B1 equal to 1. But then you would need to have in your G2 LCP solved manifold, you would need to have probably some kind of nearly Kähler solved manifold. I mean, solved manifolds are wild. So, for example, this Milner result, which excludes some Einstein condition, there are Einstein solved manifolds. So it's a kind of a big thing. So I'm not sure if it could apply directly. It's certainly interesting to think whether solved manifolds might have the structures. Yeah. Okay. As far as I remember, there is a paper by Simon was here, Simon and Anna, about conformally parallel G2 structures, and they are able to produce something. What they do is on some solvable Lie group, which is not what's it called? Not unimodular, exactly. Okay. So I don't remember if their result is a classification result, but they certainly have examples where they are actually very nice because they're non-compact, so they are able to rescale those to G2 metrics on basically on R7, which were not known in the prism. So the paper is really nice. But I don't know. I think it's called conformally parallel G2 structural solved manifolds, which is a bit misleading because they work not in the solved manifold; they just work in the solvable.
Yes, in the manifold.
Yeah.
So, okay.
But I mean, I think someone is not here anymore. He could say more about it. But in general, I don't know about. I wouldn't be so quick in excluding this.
Good. Okay, thank you.
You're welcome.
Are there any other questions for Giovanni? No? If this is not the case, let's thank him again.
Thank you again for the invitation. Thank you very much.
Giovanni, very nice talk.
Thank you.
Well, and we invite everybody to our last session of this webinar in 2 weeks' time. The speaker will be Jason Lotte, if I'm not mistaken, isn't it, Enrique?
Yes.
Yes? Okay, good. So I hope to see you all again in 2 weeks. Thank you.
Thank you. Have a nice day and evening.
Cheers.
Again for the invitation. Bye-bye, everybody.
Ciao.
Ciao, ciao.
Have a nice weekend. Ciao.